Good morning, everyone. My name is Flavia Marconi. I am a civil engineer and a PhD candidate in hydraulic engineering. In this lesson, we will focus on adaptation and risk mitigation strategies. In the previous lessons, we have seen how floods and other hydrogeological hazards are linked to land use and urbanization. Now we want to move one step further. What can we actually do to reduce these risks? Adaptation refers to all those measures that help societies, cities, and ecosystems adjust to the changing climate and its impacts. This includes both short-term actions, such as emergency response systems, and long-term planning, like sustainable land and water management. This slide gives us the roadmap for this lesson. We will begin with a definition of risk, clarifying what we mean by this term in the context of natural hazards and urban environments. Then we will move to the classification of risk mitigation measures, distinguishing among the different types of strategies that can be applied. After that, we will focus on the description of the mitigation measures, going into more detail and looking at examples of both structural and non-structural solutions. Finally, we will talk about hydrologic and hydraulic invariants, sustainable urban drainage systems, and about one of the most important measures used for flood risk mitigation, dams. In this slide, we see how risk is defined in the context of natural hazards. Risk is commonly expressed as the combination of three main components: hazard, exposure, and vulnerability. The formula here, R equals H times E times V, reminds us that risk does not depend only on the intensity or frequency of an hazardous event, but also on who and what is in harm's way, and on how vulnerable they are. Hazard refers to the potential occurrence of a natural or human-induced event, such as floods, droughts, or storms. Exposure captures the presence of people, infrastructure, ecosystems, or assets in areas that could be affected. And vulnerability expresses how sensitive or susceptible those exposed elements are, and their ability or lack of ability to cope and adapt. In other words, even a strong hazard may result in low risk if exposure and vulnerability are minimal, whereas a moderate hazard can become highly damaging if exposure is high and vulnerability is significant. This framework is fundamental for designing effective risk mitigation strategies. In order to reduce risk, we can adopt a wide range of mitigation measures, which are usually classified into two main categories: structural and non-structural. Structural measures are physical interventions, for example dams, diversions, spillways, or levees. Their purpose is to control or contain the hazard, reducing its direct impact on people and assets. On the other hand, non-structural measures act more on the organizational and regulatory side. These can be divided into active measures, such as maintenance, monitoring, and early warning systems, and passive measures, such as land use regulations, territorial planning, or urban planning rules. The key idea here is that an effective risk management strategy does not rely only on building structures, but also on governance, planning, and preparedness. Often the best results come from combining structural and non-structural measures in an integrated approach. One of the most effective long-term mitigation tools is land use planning at the basin scale. This is a non-structural measure that works on a macro scale and remains effective over long periods of time. The goal is to mitigate hazards by controlling how land is used. For example, terracing on steep slopes, as you can see in the pictures, reduces erosion and stabilizes the soil, preventing shallow landslides and debris flows. This strategy belongs to the so-called fighting approach, as it directly acts against the hazard formation. Another important tool is river maintenance. This is also a non-structural measure at the macro scale, but it is effective only in the short term, meaning it requires continuous interventions. Maintenance includes activities like removing sediments, clearing vegetation, or repairing banks. By keeping the river channel in good condition, the risk of flooding is reduced. Again, this is part of the fighting strategy, because the intervention directly reduces hazard intensity. River training, instead, represents structural measures. It is applied at the macro scale and has short-term effectiveness, since rivers are dynamic systems that constantly change. River training includes interventions like embankments, levees, or groins that guide and control the river's course. The main objective is to mitigate the hazard by modifying the channel geometry and flow conditions. As in the previous cases, this is also a fighting measure, aiming to directly control the hazard. Another classical hydraulic defense measure is levees. Levees run along rivers and are designed to keep water inside the river channel, protecting the surrounding land. These are again structural measures implemented at the macro scale. They provide immediate effectiveness, but only if they are properly maintained and monitored. The aim is to mitigate the hazard, but if a levee breaks, the consequences can be extremely severe, because water floods suddenly into the areas that were assumed to be safe. A completely different strategy is to designate areas that are intentionally allowed to flood during high flow events. In this case, the aim is not to prevent flooding, but to manage where it occurs, so that damages elsewhere can be avoided. This is a non-structural measure, effective in the short term, and applied at a mesoscale. The main goal here is to reduce exposure and vulnerability, rather than eliminating the hazard itself. The strategy is adapting, because it accepts that floods cannot always be avoided, and instead focuses on minimizing the impacts, often combined with financial compensation for those affected. Urban land use planning is another fundamental tool for risk mitigation. Deciding where to build and under what regulations directly affects exposure and vulnerability. For example, prohibiting construction in flood-prone areas or assigning safer land uses significantly reduces potential damages. This is a non-structural measure applied at a mesoscale, with long-term effectiveness, since once planning rules are in place, their influence lasts for decades. It follows the logic of adaptation, learning to live with the risk by reducing the vulnerability of cities and communities. A very innovative concept developed in China is that of sponge cities. The idea is that urban areas should be designed to absorb, store, and reuse rainwater, just like a sponge. Solutions include green roofs, permeable pavements, rain gardens, and infiltration basins. These reduce runoff, lower flood risk, and at the same time improve the quality of urban life and support water reuse. This measure is mainly non-structural, applied at a mesoscale with long-term effectiveness. It combines both adaptation and fighting strategies. It increases resilience while also reducing flood peaks. Today, sponge cities are a central element of sustainable water management policies. Civil protection is another key tool. Here we are not talking about physical structures, but about organization, coordination, and emergency response. Civil protection is crucial in reducing risk because it issues warnings, coordinates evacuations, and saves lives during emergencies. It is a non-structural measure with immediate short-term effectiveness. The scale is meso, as it involves entire communities, and the strategy is both adapting and fighting, since it acts on vulnerability but also directly addresses the hazard during the event. Individual citizens can also play a role in flood risk mitigation through self-protection. Examples include using sandbags, installing temporary barriers, or elevating valuable objects above ground level. These are small-scale, micro-level actions, but they can make a big difference at the household level. They can be either structural or non-structural, depending on the solution. Their effectiveness is short-term and tied to a single event, but they represent a concrete example of shared responsibility between institutions and citizens. Another micro-scale measure involves building strategies. This means designing houses and infrastructures that can withstand floods, for instance by elevating them, using wetproofing techniques, or constructing amphibious buildings that can float when flooded. These are structural solutions with short-term effectiveness, and they aim at reducing exposure and vulnerability. The underlying strategy is adaptation. We do not eliminate the hazard, but we reduce its impact on people and assets. Insurance schemes and public compensation programs do not reduce the hazard itself, but they mitigate vulnerability. By providing financial support after a disaster, they help families and communities recover more quickly. This is a non-structural measure that can apply at all scales, from individuals to global systems. Its effectiveness is immediate as it comes into play after the damage occurs, and it is a form of adaptation, social and economic resilience, rather than physical protection. Here I would like to introduce the concept of hydrologic-hydraulic invariance. In a natural watershed, during a rainfall event, part of the water infiltrates into the soil and is gradually returned to the river system. Not all precipitation immediately becomes runoff, because water can be stored in depressions, follow irregular paths, or spread into areas not usually affected by floods. This natural storage effect helps to reduce flood peaks and delay the flow. However, when the watershed becomes urbanized, the land use changes reduce soil permeability and channelize flows. This accelerates runoff and leads to higher flood peaks, larger flood volumes, and greater stress on the sewer system. In addition, the impermeabilization of soils increases surface runoff because infiltration is reduced or even eliminated. As a consequence, the sewer system may become insufficient even if the rain itself does not change, since it has to cope with much more water in a shorter period of time. Here we continue with the concept of hydrologic-hydraulic invariance, but now focusing on the factors that determine runoff in a watershed. When urbanization increases, several key elements are affected. First, the concentration time is reduced, because flows are channeled more quickly. Second, the infiltration capacity of the soil decreases, which means less water is absorbed and more water runs off the surface. Third, the natural storage effect, which helps to temporarily hold water in depressions or soils, is also reduced. It is important to note that the input of the phenomenon, the rainfall event, does not change with urbanization. It is independent of land use. On the right, we can clearly see these effects in the hedograph. The blue line represents the natural condition, while the orange line represents the urbanized watershed. With urbanization, the peak occurs earlier, the discharge is higher, and the flood volume increases. These changes highlight the direct impact of land use on flood risk and hydraulic safety. Here we can define more precisely what we mean by hydrologic-hydraulic invariance. Hydraulic invariance refers to the invariance of flow rates. This means that the storm runoff discharged from an urbanized area into a watershed should not exceed the discharge that existed before urbanization. Hydrological invariance, instead, focuses on the invariance of flood volume. Both flow rates and volumes of storm runoff should remain unchanged compared to pre-urbanization conditions. In practice, this means that any land use transformation which alters the permeability of the surface must be accompanied by compensatory measures. These measures are designed to ensure that the maximum discharge stays the same before and after the transformation. Let's now look at the differences between complementary and compensatory measures. Complementary measures are mainly designed to increase the soil's infiltration capacity. These include infiltration basins, which collect runoff and allow it to infiltrate later, draining trenches that enable part of the surface runoff to enter the soil, and filtering floors made of permeable materials. The goal here is to enhance infiltration, and these measures are often applied through best practice management and low-impact development strategies. However, their benefits are usually moderate, so they are more suitable when a transformed area is not very large. On the other hand, the compensatory measures focus on increasing the storage capacity of the area. Examples include oversizing water collection collectors, installing underground tanks to temporarily store excess water, preparing or extending existing drainage ditches, or creating temporarily floodable green areas. These measures are particularly important when infiltration alone is not sufficient because they directly reduce runoff volumes by providing temporary storage. Finally, I would like to introduce a modern approach, Sustainable Urban Drainage Systems, or SUDS. The main idea of them is to manage stormwater as close as possible to where it falls, instead of immediately channeling it into the sewer system. These systems include solutions such as green roofs, permeable pavements, or bioretention areas, which you can see illustrated here. The process usually follows 4 steps: infiltration, detention, reuse, and transport. This means that water is first allowed to infiltrate the soil, then temporarily stored, and whenever possible reused before being conveyed downstream. The benefits go far beyond flood risk mitigation. Here we see 2 practical examples of SUDS: rain gardens and bioretention cells. Rain gardens are shallow, depressed areas planted with grasses, flowers, and shrubs. Their main purpose is to capture rainwater from roofs, driveways, or streets and allow it to slowly infiltrate into the soil. They are simple but very effective in reducing runoff. Bioretention cells are a more engineered version of rain gardens. They consist of a depression filled with a special soil mix placed above a gravel drainage bed. This system is designed to provide multiple functions: storage of stormwater, infiltration into the soil, and also evaporation through vegetation. These solutions not only help manage stormwater and reduce flood risks, but also enhance the urban landscape and contribute to biodiversity. Green roofs are another variation of bioretention systems, specifically designed for buildings. They consist of several layers: a waterproofing layer, a drainage mat, soil, and finally vegetation layer. The main function of green roofs is to retain rainfall and promote infiltration, while the vegetation helps with evapotranspiration of stored water. In this way, they significantly reduce the volume of stormwater entering the sewer system, delaying runoff and lowering flood risks. Beyond stormwater management, green roofs also provide important co-benefits. They improve thermal insulation of buildings, reduce the urban heat island effect, enhance air quality, and even create habitats for biodiversity in urban environment. Infiltration trenches are narrow ditches filled with gravel, designed to intercept runoff from impervious surfaces such as roads, sidewalks, or parking areas. Their main role is to temporarily store the runoff and allow more time for the water to infiltrate into the underlying native soil. These systems are particularly effective in reducing peak flows and volume of stormwater, while also improving groundwater recharge. At the same time, they help filter pollutants as the water percolates through the gravel and soil layers. Continuous permeable pavement systems are designed to let rainfall pass directly through the pavement surface into a gravel storage layer below, where it can naturally infiltrate into the soil. Unlike conventional pavements, which create impermeable surfaces and increase runoff, permeable pavements allow stormwater to be managed and directly at the source. There are different types of systems. For example, porous asphalt or pervious concrete function as continuous permeable surfaces, while block paver systems capture water in the open joints between the blocks and direct it into the underlying storage zone. These systems are particularly effective in urban areas such as parking lots, sidewalks, and low-traffic streets. Another effective measure is the hydraulic disconnection of roofs combined with rainwater collection tanks. Normally, water that falls on roofs is collected by downspouts and sent directly into the drainage network. This increases the load of the sewer system during rainfall events. By disconnecting the downspouts, however, this water can instead be diverted into draining trenches or infiltrated directly into the surrounding soil, reducing surface runoff and peak discharges. An additional option is to connect downspouts to rainwater collection tanks. These tanks store rainwater during wet periods, which can later be reused for non-potable purposes such as irrigation or cleaning, or simply released during dry conditions. Another widely used measure for flood risk mitigation is the construction of dams and storage areas. Dams allow large volumes of water to be stored and then released in a controlled way. In this way, flood peaks can be reduced and the risk of inundation downstream is mitigated. These are structural interventions implemented on a very large spatial scale. They are highly effective in the short term, although their effectiveness is limited by the available storage capacity. The strategy is fighting, meaning that we try to directly counteract the hazard. Of course, dams also come with environmental and social impacts, which always need to be considered. Let's now focus in more detail on one of the most important structures in hydraulic engineering and flood protection, dams. Dams play a crucial role in water management, energy production, and risk reduction, and they can be classified in several ways. First, based on use, we distinguish storage dams, which are built to create reservoirs and ensure water supply, diversion dams, which redirect the flow of rivers for irrigation or hydropower, and retention dams, often used for flood control. Second, according to their material of construction, we have earth-filled dams made mainly of compacted soil, rock-filled dams built with large rock fragments and an impermeable core, and RCC dams, which are roller compacted concrete structures particularly strong and efficient. Finally, considering their hydraulic function, we identify overflow dams, which allow water to pass over their crest, and non-overflow dams, which do not. This classification shows the wide variety of design approaches, each tailored to specific environmental conditions, engineering challenges, and safety needs. Ultimately, dams represent not only massive engineering structures, but also key instruments for balancing water availability, energy production, and flood defense. Let's now focus more specifically on storage dams, which are among the most common and multifunctional types of dams. Their main purpose is to store water so that it can be released when needed, and this storage serves several important objectives. First of all, storage dams are fundamental for irrigation, ensuring a steady supply of water for agriculture even during dry periods. They are also essential for flood control, as they help to regulate river flows and reduce the impact of extreme events. And another crucial function is hydropower generation. By releasing stored water through turbines, these dams produce renewable energy, making them central to sustainable energy strategies. Storage dams also support navigation by maintaining adequate water levels for river transport, and they are vital for water supply, providing drinking water to millions of people. Finally, they also contribute to recreation, offering opportunities for fishing, boating, and tourism, which are valuable both socially and economically. In short, storage dams represent a strategic infrastructure that combines safety, resource management, energy production, and social benefits in a single system. To better understand the real role of dams worldwide, let's look at this chart provided by the International Commission on the Large Dams. It shows the distribution of purposes for which dams are built. We can clearly see that irrigation is by far the most common purpose, accounting for almost half of all dams, 47%. This underlines the crucial role of dams in supporting agriculture and food security, especially in regions where rainfall is not reliable. The second major purpose is hydropower, with about 21%, highlighting how dams are a cornerstone of renewable energy production. Other important uses include water supply at 12% and flood control at 9%, both essential for protecting populations and ensuring access to safe water. Finally, smaller percentages are linked to recreation, navigation, and fish farming, which still bring important social and economic benefits. Here are two other important categories of dams: diversion dams and retention dams. A diversion dam is built not primarily to store water, but to divert all or part of the flow from a river. This water can then be used for irrigation, livestock, industrial and municipal supply, renewable energy systems, or even recreational purposes. Diversion dams are also useful to reduce the impact of damaging flows by diverting excess water from one channel to another. On the other hand, retention dams are mainly designed for flood control. Their purpose is to delay and laminate the passage of floods, thereby protecting downstream urban and agricultural areas. Because of this role, retention dams generally have a large flood capacity, making them essential for risk reduction and safety. Together, these two types of dams highlight how engineering can both redirect water for beneficial uses and protect society from natural hazards. Let's move on to the material construction classification. So on one side we have RCC dams, These are dams built with the concrete, stone, or masonry. Within this group, we can distinguish gravity dams, which rely on their own weight to resist water pressure, arc dams, which transfer the water load to the valley sides, and buttress dams, supported by a series of sloping walls. On the other side, we find earthfill and rockfill dams, also called embankment dams. These are constructed with natural materials such as compacted soil or rock, and they are very common worldwide because they adapt well to different foundation conditions. This classification shows how the choice of materials and design strongly depends on the local topography, geology, and hydrology. Here is an example of the gravity dam. These dams are designed to hold back water by using only their own weight to resist the horizontal pressure exerted by the water. They are massive, wall-like structures, usually made of concrete, and their stability relies on the vertical force of gravity acting downwards. Because of this, they are considered very strong and durable, although they require solid foundations and high construction costs. Now let's focus on arc dams. Arc dams are made of concrete and they curve upstream toward the water. This special shape allows the force of the water to be transferred into the canyon walls instead of relying only on the weight of the dam itself. They are usually built in narrow valleys with solid rock foundations, which provide the necessary support. Compared to gravity dams, they use much less concrete, making them more economical, but at the same time they require very strong geological conditions. A famous example is the Hoover Dam in the United States, one of the most iconic arc dams in the world. In the end, there are buttress dams. A buttress dam can be considered a variation of a gravity dam, but instead of relying only on its own massive weight, it is supported by a series of triangular walls called buttresses. These buttresses are placed on the downstream side and act like vertical supports, preventing the dam from being pushed over by the force of the reservoir water. The main advantage of this structure is that it requires much less concrete compared to a traditional gravity dam, which makes it more economical and efficient, especially in places where construction materials are limited or expensive. At the same time, buttress dams are still very strong and stable because the pressure on the water is transferred through the buttresses to the foundation. Then there are the embankment dams, which belong to the category of earthfill and rockfill dams. These structures are built using natural materials such as earth, rock, or a combination of both. For this reason, they are usually constructed in areas where large amounts of soil or rock are easily available, making them cost-effective compared to concrete dams. What is remarkable is that embankment dams are by far the most common type of dam worldwide. They represent about 75% of all dams in the world and approximately 65% of all reported dams fall into this category. Their popularity is due to their adaptability and relatively lower construction costs. Despite being made of natural materials, embankment dams can reach impressive sizes and provide the same essential functions as other types of dams, such as water storage, flood control, and hydropower generation. Let's move on the last classification according to the hydraulic functions of the dam. An overflow dam, like the one shown on the left, is designed so that water can safely flow over its crest when the reservoir level rises above the maximum storage capacity. This makes it an essential structure for flood management because it prevents overtopping and uncontrolled failures. On the other hand, non-overflow dams, like the example on the right, are not designed to allow water to spill over their crest. Instead, they are combined with separate spillways or outlet works to manage excess water. So, while both types are crucial, overflow dams directly manage high water events, whereas non-overflow dams rely on auxiliary structures to ensure safety. To conclude our focus on dams, let's talk about one of the most tragic examples in dam engineering, the collapse of the Teton Dam in Idaho in 1976. The Teton Dam was part of the Teton Basin project, designed to provide irrigation, flood control, and hydropower and drinking water. However, during its very first filling, the dam experienced a catastrophic failure. Within hours, the structure was breached, releasing massive amounts of water and causing widespread flooding downstream. Investigations revealed that the failure was mainly due to design and construction deficiencies. In particular, the impervious core of the dam cracked, leading to internal erosion and hydraulic fracturing of the fill material. The project was also affected by pressure to keep to the construction schedule, which meant that important foundation treatments were not adequately carried out. So this disaster highlights a crucial lesson. While dams are essential for society, their design, construction, and maintenance must follow the highest safety standards. So the collapse of the Teton Dam remains a reminder of how even small oversight can lead to catastrophic consequences. Another tragic case in dam history is the Vajont Dam disaster, which occurred in Italy on the evening of October 9, 1973. The Vajont Dam itself was an engineering masterpiece, one of the tallest dams in the world at the time, located near the town of Longarone in the province of Belluno, in the Veneto region. However, the disaster was not due to a structural failure of the dam. Instead, it was caused by a massive landslide. Over 260 million cubic meters of rock and debris fell from the northern slope of the Mount Toc into the reservoir. The enormous volume of displaced water generated a gigantic wave which overtopped the dam and swept through the valley at incredible speed, destroying entire villages and causing thousands of casualties. This event shows that even when a dam is structurally sound, the surrounding geological and environmental conditions are just as critical. Here I want to highlight the main references on this topic that can be useful. The first one is the European Commission's webpage on green infrastructure. This is a valuable resource for understanding how nature-based solutions such as restoring wetlands or creating urban green spaces can support climate adaptation and biodiversity protection. The second reference is a report by the European Environment Agency, published in 2020. It focuses on how the agricultural sector in Europe is adapting to climate change. Since agriculture is one of the most vulnerable sectors, this report provides concrete examples and data on adaptation practices at the European scale. Then we have the IPCC 2022 report on climate change impacts, adaptation and vulnerability, which is one of the most authoritative and comprehensive assessment. This report summarizes global scientific knowledge and helps policymakers understand risks and plan effective strategies for the future. Finally, the Global Assessment Report on Disaster Risk Reduction by UNDRR. This is a global outlook that looks not only at climate change but at all types of disasters, with a strong emphasis on reducing vulnerability and increasing resilience. Thank you very much for your attention.